Okay, so welcome back everyone, and apologies for the delay. So today it's my pleasure to welcome Nathan Doumèche, who will be talking about physically informed machine learning as a kernel method. Yeah, thank you, Nathan.
Well, thank you very much for the introduction, and thank you for having me. Actually, I'm very happy to present to your community the result that we had. So you can find the slide on my website if you want to go back, or if you miss a technicality and you want to make sure to understand everything. So you just go to the nathandoumèche.com section research, and there is actually the slot for the seminar of today, and you can find the slides over there. Okay, so without further ado, so yeah, today I'm going to talk about the mathematics of physics informed machine learning, and so the different results that I managed to prove during my PhD. So, sorry. Okay, so this is a joint work with Francis Bach at INRIA Paris, Gérard Billot and Claire Boyer, who are actually my PhD advisors at the Sorbonne University. Okay, so here today the menu is as follows. So I'm going to start by introducing a little bit what I'm going to talk about when I talk about physics informed machine learning. So here PIML. And then I'm going to present the results that we proved regarding the consistency of physics informed neural networks. But this result didn't manage to understand the impact of the physics in terms of speed of convergence, and so we pushed them a little bit further using the kernel learning machinery. And so then for those of you who are not familiar with kernel learning, I'm going to introduce a little bit the notion, and afterwards I'm going to present the link that exists between physics informed machine learning and kernel learning methods, with the aim of proving that the physics can help boosting the speed in statistical learning. Okay, so I really like when people interrupt me to ask questions, so really don't be shy about it. I mean, if you have something in mind, a question, anything that you didn't understand, I mean, I'm really happy to take an extra minute and to answer the question. Right, so let's start by introducing a little bit what I mean when I talk about physics informed machine learning. So I've watched the seminar of last week, and so I know that you're aware at least a little bit of what it is, but to make it a little bit clearer, I understand that physics informed machine learning is a whole framework when you're trying to mix the methods of machine learning in terms of statistics with some physics knowledge that usually takes the form of partial differential equations. Okay, and so it's very interesting for both communities. For the statisticians, it's interesting because it can give more interpretability to the models, and hopefully it can speed them up. Whereas for the people from PD's community, it's interesting in terms of creating new tools to solve PDE, and perhaps to give some tools that are useful in ill-conditioned case. And I'm going to specify a little bit further what I mean by that. So as I said, there are three kinds of physics informed machine learnings, three setups that are really common in the community. So the first one is really simple to understand, that you want to solve a partial differential equation over some domain, and specifying a set of boundary conditions. And so typically the initial paper of physics informed machine learning was by Raisi and colleagues of 2019. And so they give the example of solving, for example, the Schrödinger partial differential equation that's written over there, and the periodic boundary conditions, and with a specified initial condition. And so they managed to do that using physics-informed neural networks. So I'm going to present the techniques afterwards. But yeah, so the first case is to have some kind of generic solver of PDE. The second one is what I call hybrid modeling. Well, not just me, but what I usually call hybrid modeling. It's when you mix some data and some known beforehand physics priors. So typically, there was a nice work of Kayet colleagues of 2021 when they want to model the heat transfer in some uranium bundles. Okay, so typically you have a uranium plant that's producing electricity and works by making some uranium bundles over there heating and heating some water and goes into the chamber. The problem is that sometimes the reaction of the uranium is can be a little bit extreme, and it can be dangerous for the plants. And so you need to monitor the temperature of the whole core. But the problem is that the typical heat, the typical temperature of the bundle is too high to simply put sensors on the bundle, because they will melt actually. And so you need to have another way to measure the heat, the temperature of the bundle. And so typically you're going to measure the temperature of the water that's surrounding the bundle, and you're trying to backpropagate the whole measurements to deduce the temperature of the bundle. Okay. And so here, typically what you see in the figure is that you have the orange dots over there that are going to be the sensors, and you're trying to reconstruct the whole flows of temperature. And so here you see that you have a mix of data measured at the sensor points and of some prior physical knowledge that's going to take the form here of the Navier-Stokes and diffusion equations. That you may know or may not know, but that's going to be written as a sequence of differential operator here, D1, D2, D3, and D4. Okay, and so in the hybrid modeling setting, what you really want is to mix the data that you have here with the physical prior knowledge of the partial differential operators over there to construct an estimate of the overall temperature in the liquid. And so finally, the third use case of physics-informed machine learning is the inverse problem. When you observe at some point a function, over there it's the function u of t and x, and you try to learn the coefficients of the partial differential equations that might give rise to such a function. Okay, and so typically this was initiated by Rice and al. Since in 2019. And so you see here that they managed to reconstruct the coefficient pretty well of this given PDE. Okay, and so regarding the three use cases here in this talk, I'm going to focus on the second one, so the hybrid modeling setting. So regarding physics-informed machine learning and the three use cases, there have been plenty of papers, a lot of them experimental, showing very good results and very interesting avenue of research. But still, the theoretical foundations of physics-informed machine learning are still a bit scarce. And so it's interesting to know whether or not the algorithm that are proposed by the literature are can be shown to have good theoretical properties. Okay, what I particularly like about hybrid modeling is that it's useful in ill-posed settings. So typically, you know the partial differential operator here because you know the physics of of your function. but you do not necessarily know very well the boundary conditions. Okay, and so in the general PD community, it's a nilpost problem, and so you cannot give some directly a solution to this PDE because you don't have the whole set of boundary conditions. And so here you try to incorporate some data to try to alleviate the nilpostness of the problem. Okay. And so typically here, it's going to take the following form. So you have some target y that's going to be a function f star of the features that you can measure x plus some noise, epsilon over there. And so you're trying to estimate f star using both the supervised learning setting of some data over there, x, y, and y, so you have n data, and you're trying to mix it with some prior knowledge of a partial differential equation, d, that's going to be approximately followed up to some modeling error, you say, okay, because most of the time in physics, you're trying to approximate the behaviors of your function, but you're doing some approximation, so there might be some error in the modeling. Okay, is it clear for everybody what we are going to study here? No answer is a good answer. Okay, great. So to give another example.
Hello.
Yeah, hello.
So instead of the boundary conditions or initial conditions, you use the data itself to represent them implicitly.
That's a way of saying it, yeah, definitely. So there are some models when you can directly add the boundary, an incomplete set of boundary conditions and initial conditions. But here in the general setting, you're trying to add some data with the hope that it's going to replace in some sort the boundary conditions, and that it's going to correct the fact that you have some modeling error.
So the physics prior knowledge is by solving this equation that I see here, D, F star.
Well, you see, in general, it's very difficult to solve the PDE. For example, if you think of Navier-Stokes. And so you're not trying to give an analytic solution of it, but you're going to, I'm going to present this afterwards, but we are going to give some numerical approximates of such solutions. Okay,
but
that's going to match at best your data. Yeah?
This will constitute the prior knowledge, that solution, empirical solution.
Yes, yes,
okay,
that's the idea, definitely.
Perfect.
Thank you for your question. Okay, and so here, for example, another example is to model an neuronym. So here you see a vein in the brain, and the little ball that you see over there, this growth, it's what's called a neurorhythm. It's an abnormal growth in a vein in the brain, and the problem is that it's going to grow bigger and bigger up until the point that it might break, and this is very deadly. But sometimes it just stays as it is if the pressure is not high enough. And so before doing some surgery on the patient, it's interesting to know whether or not the aneurysm is dangerous, because the surgery in itself is very deadly too. And so it's interesting to be able to model the pressure field in the blood vessel, given this the geometry of the vessel. Okay, and so typically here you know that it's going to satisfy up until the approximation that it's Newtonian fluid, the Navier-Stokes equations, and you can collect some data in the vessel. And for example, Arzani and colleagues, they showed in 2021 that they managed to recreate pretty well the pressure field and the velocity of the blood inside such vessels. Okay. using a little set of data. Great. So here we're going to do the math of the problem. And so we need to be able to model it simply. And so we're going to add some notations. So typically we're going to call omega the bounded set on which the problem is posed. Okay, so here it's going to be the gray set of the blood vessel. Remember that we're calling f star the unknown target function, and d curl the differential operator that's approximately followed by your solution. Okay, and so you were asking basically, okay, so that's the goal, but how are you going to do that? And so an interesting algorithm that's been proposed recently is the physics-informed neural networks. And it relies on 3 sampling, okay? So typically, if you have a knowledge of the boundary conditions, you are going to sample a first set of points on the boundary of the domain, omega, that you sample as much as you like, that you're going to call the condition points. Once again, you are going to sample another set of what's called collocation points inside domain omega. Here it's going to be the yellow crosses, where you're going to enforce your solution to follow the partial differential equation. And finally, there's the training sample of your feature X and your target Y. Here that are represented by the orange dots, on which you have no control a priori. I mean, they might be expensive to get, and maybe they might be restricted in a sub area of the whole domain. But these points, you do not have control over them. And so, given this whole set of points, you are going to try to minimize a risk function, or if you're from the machine learning community, a loss. That's going to be threefold. So the first one is a data fidelity term. So you want the function that the best candidate is the one that's going to first minimize its distance from the data that you observed. Then it's going to minimize the distance from the boundary condition function h that you've supposed. And it's going to minimize the whole sets of partial differential operators on the collocation points. Okay, so if I go back to this slide, you see you have sampled 3 sets of points, and you want to find the candidates that's going to minimize the risk computed over these specific points. In practice, what you do is that you're going to minimize this empirical risk over some parameterized set of function. And so here we denote by theta the parameters, okay? And so typically, what's done in practice is that you choose a neural network architecture, so that's directly parameterized by its weights, and you can easily compute its derivative using what's called the auto-differentiation algorithm. And so that's very specific to neural networks, and that's why they're successful. It's because it's really easy to compute the derivatives of neural networks. And so here we leverage this whole knowledge about differentiating neural networks that's been developed for years in the neural network community to actually compute the partial differential operators applied to a neural network. Okay, and so typically the loss that you're going to present is the sum of these 3 losses, and you're trying to find the parameters that are going to minimize the following loss. Is it clear for everybody the whole PINN setup, or are there some questions up here? Great. Okay, and so here in this talk, we're going to focus on an architecture of neural networks that's dense. That means that all the weights are linked one to another, and that rely on the activation function that is the hyperbolic tangent. Okay, and so if you don't know, a neural network is just a series of linear operation represented by the lines over there, which gives each time a result to which you're going to apply a nonlinear function, here the hyperbolic tangent. Okay, and so typically when you're trying to optimize the neural network to find the best parameters, you're going to find some minimizing sequence of parameters here, theta hats, that are going to minimize the empirical risk. So here you see that the empirical risk has several parameters. So n is the number of data, ne is the number of points you've sampled on the edge to enforce the boundary conditions, and nr is the number of regularizing points inside of omega used to enforce the partial differential operators. Okay, so that's how it's done in practice. And so when you do that, you do it with the hope of actually minimizing the theoretical risk that's integrated over the whole domain omega. Okay, and so a natural question to ask regarding the physics-informed neural networks setting is whether or not minimizing the empirical risk that's discretized is going to actually minimize the theoretical risk that's integrated. Okay, you can notice that the discretization is needed to be able to compute it on a computer, because you cannot, you can only approximate integrals on the computer. Okay, and so you hope that sampling enough points, you're going to actually approximate well the integral over there. And so this idea that minimizing the empirical risk, the discretized version of the risk, is going to minimize the integrated version of the risk, of the theoretical risk, this requirement is called the consistency over there. And if you're from the machine learning community, you may know the reverse case. When it's not consistent, we say that it's an overfitting case. Okay. And so the first question that we're asking is whether or not the physics-informed neural networks are consistent, and the answer is no. So it's a bad news for physics-informed neural networks that if you do nothing, it's possible that you're overfitting. And so we provide in the paper on the convergence of PINNs a counterexample where actually the empirical risk measured on the points there is 0, but the theoretical risk is infinite. So it's very simple. You have a model, U star, that's a target function, sorry, U star, that's going to satisfy the partial differential equation that if you derive it twice, plus the first derivative is 0, and so you know that then U star is a decaying exponential. You want to enforce your solution to satisfy the PDE on the red cross over there, and you measure some data that are the blue points over there, and you can actually create a function that's going to be piecewise constant. And so you see that if it's piecewise constant, then on the right cross, its derivatives of 0, okay? And so the differential operator evaluated over there is always 0. And you perfectly fit your data set with the noise, as shown on this example. But you see that it's really not what you want to do in the physics-informed setting. And so we have developed then some techniques to make sure that this doesn't happen. Okay. Actually, what you see here is that the pathological functions that are going to minimize the empirical risk, but which have an infinite theoretical risk, or all have some infinite derivatives there. You see, they have jumps. And so we thought that if we make sure that the solution that we construct doesn't have jumps, then maybe we avoid this pathological case. And what we have shown, and that's interesting, is that you can actually bound the norms of the derivatives of a neural networks by the L2 norm of its weights. There's some kind of formula that you can see here, but the idea is very simple: is that if you have weights that are bounded, then the derivatives cannot explode, and you do not see these jumps over there. And so what we've proposed is to add to the empirical risk a ridge penalty, okay, that takes the form of a hyperparameter there, lambda ridge, plus multiplied by the L2 weights of the parameters. And so it's very easily implemented in all the neural networks library as weight decay, actually. And so it's very easy to do in practice, I mean. And so we've shown that you can actually compute a decay for the ridge hyperparameter, so that when you let the number of penalty points go to the infinity, minimizing the empirical risk penalized by the ridge penalty will indeed minimize the theoretical risk, so with the integrals over the whole set of neural networks here. So we've called NN for neural networks. H is the number of layers, and D, it's the width of each layers. Okay. And so this is true for what we call polynomial operators that are very general. It encompasses any linear differential operators and other well-known operators, such as the Navier-Stokes equations, or the Burger's equations, or I mean, basically any PDE that I've seen, but maybe you are studying very specific PDEs that are not polynomial. But here, what's important to see is that the consistency of PINNs there, it's ensured for basically any PDE that you might see in practice when you're penalizing by the ridge penalty. And we've shown another interesting thing is that when you let the size, the width of your neural networks go to the infinity there, you're actually minimizing over all smooth functions, meaning that there's no bias intrinsic to the neural networks class of function, okay? And so this means that the neural networks, the dense neural networks using the hyperbolic tangent activation function is a good choice to optimize the PINNs problem, because it has no bias. Okay. But then what people want when they want to solve a PDE, for example, is that they want to the neural networks to actually converge toward the true solution of the PDE. And the weakest norm that you can ask for is the L2 norm on omega. And we've shown that only the consistency of the risk is not enough to have this nice property. There's a counterexample there. Which shows that, for example, if your boundary and initial conditions are all that you suppose that it's equal to 1, and if you enforce the advection equations, then independently of the real distribution of your data, you are always going to converge to 1. This means that when you add the physics penalty there of the boundary condition and the PDE, it's too strong. And you can only solve this PDE. And if you have an imperfect modeling case, so for example, if your true function was 1 plus cosine of x divided by 1,000, for example, you will never learn it. So you're stuck with your model. And so that's bad in terms of statistic properties. And we've shown that a way to prevent that is to add what's called a Sobolev regularization, meaning that you want to add in the risk the weights of the derivatives once again to ensure that the derivatives are going to stay bounded. And so in the theoretical risk, it takes the form of this what's called the Sobolev norms, which is the integral of the derivatives of the function. In the PD community, it's known as to enforce what's called the coercivity of the risk, and to show very nice property. And this shows very nice property of the risk when it's coercive. And what we've shown in this case, and then we will change the topic. So this is the hardest part of the talk actually, is that you can define what we call the physics inconsistency of a function, meaning it's the gap between the model that you've supposed and the function that you see. So here you see it's the integral of your function minus the boundary condition that you've supposed, and it's the integral of the differential operator that you think are going to be 0. Okay, and we showed that when you penalize both by the Rich penalty and the Sobolev penalty, when the PD is linear in this case, so it's a bit more restrictive than before, you actually satisfy two conditions that are typical of hybrid modeling, because hybrid was a mix of physics and statistics. So here the first one is the statistical condition is the one that shows that you are going to converge to f star at the speed at least 1 over square root of n. So that's good. And that the physics inconsistency, so the gap between the function that you reconstruct and the model that you've made, is bounded by the modeling error that you've made at the very beginning of the process. Okay, and so we've shown here that PINNs, they both manage to be statistically consistent with speed of convergence and to satisfy the PDE that you've enforced. Okay, so here it's our last results on PINNs. Specifics to PINNs. Is it clear still, or do you have some question over this part of the talk?
What is PI?
PI is the physics inconsistency. Okay, so that's mean that the
Thank you. It's not the path integral. Okay, thank you.
Yeah. You're very welcome. Thank you for your question. Okay, and so if you want to have a look on the paper, it's available on arXiv under the name of Convergence and Error Analysis of PINNs. Okay, so here we've seen that statistical and PD models can successfully complement each other, and that there is an algorithm, so physics of neural networks, that can be probably shown to converge towards something interesting in terms of theoretical properties. Okay. What we're going to show next is that the whole physics-informed machine learning setting of hybrid modeling can be seen as a kernel method. And this is very interesting because here, in this equation over there, you do not see the impact on the physics in terms of the speed of convergence. Okay, it's always 1 over square root of n. I mean, independently of the physics and whether or not you've taken a good or bad physics. This is because when you have more and more data, I mean, you're going to converge toward the right solution. But we were not satisfied by that, and we wanted to know, to quantify whether or not the physics can help not only ensuring that the solution that you reconstruct is not physically inconsistent, but also to help to convert more quickly toward the right solution of your problem. And so to do that, we've shown that hybrid modeling, in this case, it's a kernel method, but and that you can leverage some interesting tools from kernel learning theories that are useful to show precisely that, knowingly that the physics helps when trying to learn the problem. So for those of you who do not know what's a kernel learning method, I'm going to present it a bit quickly over there. So I think that if you're familiar with machine learning or with statistics, you're all familiar with the linear regression and with the rich linear regression. So typically you have your input X, your output Y, and here you suppose that Y is a linear function of X, so it can take the form of a scalar product between of X with some parameters beta up to some noise. Okay, and you may or you may not know, but so the next thing to do is that you're trying to minimize the following risk that takes the form of a data loss, so the gap between yi and a model, plus some rich penalty that ensures that your coefficient beta that you reconstruct do not explode. Okay, and so this is called the rich linear regression setting. And what's interesting is that it's very easy in this setting to compute the optimal beta that actually minimizes this loss given your observation X and Y. Okay, you have this very nice formula that's only a matrix inversion. Okay, and so what we call kernel learning is a very natural extension of this setting. It's when you actually transform the coordinates on which you're trying to learn a linear regression. So the simplest example for that is that, I mean, if you want to learn a function that depends on the radius, for example, in dimension 2, you can change the coordinates from x1, x2 to x1 square and x2 square. And then the problem becomes linear because you know that the radius is x1 square plus x2 square. Okay. And so here, in this setting, the kernel, so you have a map, sorry, to begin with, you have a map phi that links the initial coordinates and the final coordinates. And we call kernel the quantity that's given by the scalar product of this between two of the set of coordinates over there. And we can show that doing a linear regression in this setting is only going to involve the kernel K over there. So I'm going to make this a little bit clearer. So you have exactly the same setting as before, except that now you have a map phi here, so that you suppose that y is the scalar product between phi of x and a parameter beta that you want to learn. And you can show once again that the best parameter beta hat there is given very simply by this matrix over there. Okay, and so you see that, I mean, transforming the coordinates of your problem, I mean, it's no big deal. I mean, you have an explicit formula to actually compute the best estimator that's relevant for your problem. What's very interesting in this case is that if you work in a very high dimensional setting. So if your coordinates are in dimension d with d very large, there's some kind of trick in the optimization process so that actually the overall complexity of the kernel learning methods is only dependent on n. So the number of data and not on d, the dimension, as long as you know how to compute the kernel very quickly. So the scalar product between the maps. So that's what's called the kernel trick, is that you can, I mean, change the order of the matrix multiplication so that the complexity of your algorithm does not depend on d, but only on n. So that's a very nice property of kernel. If you're working, for example, in infinite dimensions, you can actually compute it on the computer because it's only going to depend on the data that you have of a finite number of operations. And so you see, it's interesting because here I've presented the kernels from the map perspective. So you want to do some kind of a linear regression under a deformation of your coordinates that's given by a map. But the reverse is also possible, knowingly that if you start with the kernel, so a positive definite function there, you can actually deduce from that a map, and the whole setting stands still. And so there's this big duality between kernel and maps, which simplify the whole theoretical background of it. And we call reproducing kernel Hilbert space, so RKHS, the space of the functions that are representable by the kernel. So it's a bit abstract and everything, but basically it's just saying that here the space of RKHS is the space of the map. It's the whole function that you can represent with your map. Because you see that if you have some maps that are always zero, for example, you represent nothing. Okay, so you have to satisfy some good properties of the maps for the kernel theory to be interesting. And so that just means that you're going to look at the functions that are representable by your map. And this space of function is called the RKHS. Okay. And so it's very satisfying because whenever you're trying to minimize a loss, that takes the following form. So you see a data fidelity form plus a penalty that's a L2 norm in the Hilbert space of the RKHS. Then you have an explicit formula to compute the minimizer of this problem, and so you can actually study it very easily. But you see, the whole difficulty in the kernel learning theory is to be able either to compute an interesting kernel K or to exhibit a map. Okay. So the whole difficulty is hidden there. It's to be able to show that your problem that you're studying, here the physics info machine learning setting, can be represented by a map or by a kernel. Okay, and when you know that, you have the whole theory that's for you. And in particular, you can compute the speed of convergence using what's called the integral operator. That's nothing but the function that the operator that, given a function f, associate the integral of this function with respect to your kernel. And so this object, it has eigenvalues. And if you know how to bound these eigenvalues, then you bound what's called the effective dimension of your problem. And you can compute the convergence rate of your kernel method. Okay, so the whole idea now that I've presented this to you is to show that physics info machine learning methods for hybrid modeling they are actually kernel methods. So that's the first thing we want to show. And then we want to show that we know how to bound the eigenvalues in this case to derive better convergence rates than what we've shown before. Okay, so that's what I just said. So here you hope, so you remember that the theoretical risk that we've shown, that we've studied before, was as followed. So a data fidelity terms plus some norm, that's the Sobolev norm, and the norm of the differential operator over there. And so we want to show that this norm is actually given by some RKHS, and that it helps speed up the process. Here we are going to focus on linear differential operators because that's where it works. A technical point, but that's very not difficult and not a problem, is that we are going to restrict ourselves to periodic functions, f, but it's very easy to show that actually any periodic function can be restricted on the function omega, and that reciprocally, any function defined on omega that's in the Sobolev space can be extended into a periodic function, okay? So it's only a technicality that helps us in the process, but it's no problem. And so here you see that the empirical risk become the sum, so the data fidelity terms plus the Sobolev norm of the extension plus the norm of the differential operator applied to the function on the domain omega. Okay, is the motivation clear here, or is it, if there's some kind of point that you want to, someone want to mention?
I had a question regarding modeling of the aneurysm that you spoke about, and how we can model the problem to understand how much risk there would be in terms of that abnormal growth. I'm trying to understand that, are we actually going to estimate any probabilities from this kernel trick in the PINN method? Because if you're imposing that this is going to be a periodic function in a nonlinear scenario, I don't know how much that is true in terms of real life physical systems.
No. As I say, here, for example, you see on omega over there, the blue line, you can define a function. Okay, any function that you like. And what I say is that there is there is a theorem that's called the Sobolev extension theorem that states that whenever you have a function defined on a regular domain omega, you can extend it. So here you see the extension over there, so that it becomes periodic, the extension, okay? But on your initial set where you wanted to study your problem, it was not periodic at all, okay? But just you use the fact to simplify the computations afterwards, that you are going to study to show that it's a kernel, these extensions, okay? But typically for the aneurysm, let me go back to it's a bit far away, sorry. Here, you can suppose that you have any function defined on the gray area here, okay? And then you take a square that surrounds the gray area. And what I'll tell you is that you can enforce, you can define an extension of your function, which is going to be periodic, but periodic on the square, not periodic on the aneurysm over there.
So it's a decomposition of the function into periodic sections.
If you like, yeah, you can say that, yeah, definitely, because you can show that the periodic extensions admits a Fourier decomposition, and so basically it's the same as asking for the Fourier decomposition of your initial thing. So it's nothing fancy, I mean, in the end.
Thank you. Thank you so much, Nathan. Thank you.
You're welcome. Yep. So I come back to where I was. Okay. So yeah, if you prefer it this way, you can just say that you're studying a function in the Fourier space, and that the whole Fourier decomposition thing works. I mean, that's what we showed basically. And so we shown. So here this lemma is technical, so you don't need to understand the details of it. But we show that there is here a map that we call the O of n to the power -1/2. That actually link your function to the Sobolev space here, so that the norm of the map is the right one. So the norm of the physics-informed machine learning setting. Okay. So you might ask, it's a bit strange. Why do you call it -1/2? It's because the -2, so the ON operator, has very nice properties, and so the map that we look is only the square root inverse of a positive operator that is compact, and so that emits. This shows mathematically that it emits a nice decomposition. Okay, and so morally, this is very easy to see. I mean, you just say that f of x is f scalar the Dirac delta function applied in x, and that the map is nothing but applying the operator on one side and the transpose on the other side, the adjoint on the other side. And since the original operator O of n is compact, we know that it emits eigenfunctions and eigenvalues. Okay, so you can just call it, write it as On applied to f. It's the sum of its eigenvalues with the scalar product of f and the eigenfunction multiplied by the as weight of the eigenfunction v. Okay, and so this is all technical. It's not very interesting for you to delve into, but what's interesting is that you can then express the kernel directly as a function of the eigenvalue and the eigenfunctions of this operator. Okay, so what we've shown is that when you deal with linear operators, you can represent the physics-informed machine learning penalty as a kernel norm, that the map is given by the operator O -1/2, and that you can compute using that the kernel given the eigenvalue and the eigenfunction of O of n -1/2. Okay, so these results say that there is a link between physics-informed machine learning and kernel theory. And so if you remember, kernel theory, it's nothing but linear regression over a deformation of the space. So here you see that the space, it's a space of function, so it's huge, a bit more complicated to study. But basically, what we're saying is that physics-informed machine learning is nothing but a linear regression in some abstract, complicated space. Okay. But the problem here is that evaluating the kernel is not straightforward, because we've written it as a sum of eigenfunction and eigenvalues of a potentially complicated operators. But what we've shown is that actually it satisfies a PDE in itself. So there's some kind of logic in that, is that when you penalize the problem by a PDE, so in the whole physics-informed machine learning setting, this means that the whole setting is determined by a kernel that satisfies itself a PDE. And so here you have the weak form of the PDE written over there. So if you're not familiar with weak PDEs, don't worry about it. The whole message there is that physics for machine learning is that you can actually compute an analytical solution directly without using PINNs or nothing, but you have to solve some kind of PD. So it's not easy to do, but sometimes you can and sometimes you can't. And if you remember what I told you before, when you know that something is a kernel, so a linear regression in some abstract space, you can compute the convergence speed given what's called the effective dimension. That's a function of the eigenvalues of an operator that's determined by your kernel. And what we've shown here in the article is that over a very mild assumption on the hyperparameters of your problem and on the noise. So typically, this is true whenever the noise is Gaussian, not necessarily independent from X. For example, you can have heteroscedasticity. Whenever it's bounded, it's going to satisfy, whenever it's Poisson, okay, so it's going to satisfy what's called a sub-gamma property. And in this case, you know that the error between the kernel estimator, that's minimizing your loss, and the true function is bounded by so the Sobolev norm of your function, the modeling error here, the operator D applied to f star, some properties of the noise, and the effective dimensions of a problem. And what's interesting is that these bounds are holds for n fixed. Okay, so they are not asymptotics. And so directly using that, you can improve. So you know that beforehand we had a bound on of the form 1 over the square root of n. And now you know that if your function belongs to the Sobolev space of order S, you have a bound of n to the power minus 2s divided by 2s plus d. Just using that. And so this is a very interesting bound because it's called the Sobolev minimax rate. And in the whole generality, it cannot be beaten. It's the best bound that you can give without further assumption. It's a very beautiful theorem. I think it's Sibakov who showed it, saying that if you have a function that's only differentiable s time, then you cannot approximate it more quickly than n to this power over there. So this is great. I mean, this means that PINNs they manage to satisfy the Sobolev minimax rate, and so that's a very good start. Okay, but the thing is that here you see that there is no assumption on the physics. Once again, it's only the smoothness of your function, and so we wanted to go a little bit further, and we've shown.
Nathan, can I ask you a question on the previous slide?
Yeah, go ahead, of course.
So here, if you take D to be 1 and S to infinity, that bound is giving you something like 1 over n, right?
Yes, definitely. It's the parametric rate of the central limit theorem, for example.
But if the problem is very regular and if you use a very regular kernel, you can easily beat that bound. Because in dimension 1 over n is like the field distance between collocation points. And the convergence rate that you can achieve is typically HS if you use a Mattern kernel. So it's good over n to the power s. But
I think that when you do that, you suppose that your target function is representable directly by the kernel Archeraich's space, don't you? And so you must suppose that you are more regular than only being smooth. I mean, I think you're restricted to some.
Yeah. You're assuming enough regularity on the target function.
And so I think you're assuming more regularity, and so this is why you have this this gap.
Oh, what you're saying is that you're not assuming any regularity on F?
Yeah, here the only regularity on F that you suppose is that it's S time differentiable. Here.
Yeah, but then if it's S time differentiable, if it's in HS, you should be able to achieve at least 1 over n to the power S over 2. Because you have enough regularity to achieve that. I mean, those are sampling inequalities, right, that you find in kernel methods. I don't want to I don't want to sidetrack your talk. We can talk about it later.
I mean, go ahead. But here, what I know is that when you have some noise, and when you are only looking for some function that lives in the Sobolev space H of S, when it's your only assumption, then the best rate that you can have is this one. It's called the Sobolev minimax rate, and I mean it's a theorem. It's proven. I can show it. And so
okay.
if you want to have quicker rates, then you need to have more assumptions. I mean, it's
so if you have no noise, then you can achieve better rates.
Oh yeah,
so
if you have no noise, you can go away quickly.
Okay, got it. That's because of the noise then.
But if you have noise, you cannot do better. I mean, it's I'm sure that.
Yeah.
If you have no noise, it's a whole other setting of approximation, whole other community. But yeah, you're right. If you have
for PDEs, you don't have noise, so in principle, you could beat that rate easily.
Yes, definitely. Yes, of course. You're right. But here in the hybrid modeling setting, we suppose that you have PDE and some data with some noise. And so that's what we did that. But in another setting, if you have perfect data, then maybe you could use some different algorithm, but it's not the setting that we've chosen here. But thank you for your question. It's very, it's always tricky, the rates, when someone shows you a rate, because it depends on the assumption that you've made. And it depends on also on the complexity that you like. And so it's always to be taken carefully when you when you see a rate, and so it's always good to question it. I mean, in some sense. Yeah. So we've shown that it satisfies the Sobolev rate, but here you see that we wanted to see whether or not adding some further assumptions, we could see some impact of the physics, for example. And so here what we've shown is that the interesting eigenvalues, so it's a technical lemma once again, but I wanted also to show you what we've done mathematically, if you're interested. If you're not a kernel trick fan, I mean, you can just pause for a second. It's not it's not important, but you can bound it by some interesting operators here. That's the projection over omega times the initial operator On and the projection operator on omega. But these eigenvalues are determined by some other interesting operators. And in fact, I'll show you afterward, but we know how to bound these operators in some specific case. And in particular, we know how to characterize the eigenfunctions of these operators. So they satisfy the following PDE. So don't look at it too closely, but it was just to show it to you that we can actually determine such a PDE. And so here, if you were lost before, you can go back now, because here's an example that we've made. So if typically you look for a very simple PDE, so the goal here is not to say that it's an interesting one, but it's to say that it can be done in practice sometimes. So you look at the very simple PDE, d over dx. So you suppose that d over dx of f is small, and so your function that you want to reconstruct is approximately constant. Okay, that's the hypothesis that you suppose in your problem. So you're in dimension 1, the domain is a segment, and so here you only need to suppose that your function is differentiable once, and so that it belongs to the Sobolev space of order 1. in the hybrid modeling setting, you want to minimize the data loss there, plus the Sobolev norm, plus the integral of the first derivative of f, then because you suppose that it's going to be small. And we've shown that even in this very simple case, the kernel is very difficult. It's very complicated, but still it can be computed. And it's this magnificent sum and multiplication of hyperbolic sinus and cosine. Okay, and so you can see it plotted over there. So you see that here it's the kernel associated with the Sobolev space directly, but here you remember that we've added some physics there, and you see the impact on the physics on the kernel. It's a little bit more convex. And we've managed to bound the eigenvalues of the integral operators. They decay in 1 over m squared, basically. And so we've shown, so that's the theorem that, that's the equation of this talk. I mean, if you can just look at it and understand. So the error of your function, of your estimator, okay, it's going to be of the following form. So you have the modeling error times the Sobolev minimax rate. So this is normal because if you take any function in the Sobolev space, it has some modeling error. And we know that you cannot approximate it quicker than this rate, the 1 over 2/3. It's when you take 2s divided by 2s plus d, it gives 2/3 in this case. But what's interesting is that when you have made no modeling error, so when you are actually a constant, you learn at a speed of 1 over n. So the parametric speed that's given by constant. So this is not surprising, of course. But what's interesting is to see that the physics-informed machine learning setting, it managed to learn your target function at the best speed possible, adapted, and it adapts to the modeling error that you've made. And you see here that in front of the Sobolev minimax rate of minus 2/3, you have the modeling error. So the lower the modeling error, the lower the error at the Sobolev minimax rate. And if the modeling error is 0, if you made the perfect model, then you have the optimal speed given the class of function restricted to the fact that they actually follow the PDE exactly. Okay, and so you have the whole continuum of possible rates that are well satisfied in the physics-informed machine learning setting. Okay, so that's basically what I say, that the parametric rates of 1 over n when the function f star is constant, and the Sobolev rate otherwise. So to conclude, we've shown here that physics-informed machine learning can be set as a kernel method. That in some case, you can actually compute everything, the kernel, the convergence rate, and that here it's the first result that theoretically shows that adding physics to the problem not only helps creating more interpretable physical solutions, but it also helps you learning more quickly the target function. Okay, and so the full paper was accepted at COLT 2024. So you might see me in Canada this year if you if you're a fan of things, and you can find it on archive on this number. So as I said before, you can find the slide on my website, and so thank you for your attention. So if you have further questions, I'd be happy to answer them.
Yeah, thank you very much. Thank you. Any questions? Yeah, sure. Go ahead. Yes, either Human or Reagan. Yeah.
I will let Reagan ask first.
Okay, thank you. Can you hear me, right?
Yes.
Yeah, thanks for the nice presentation and the way you're explaining the kernel method. I wanted to know, is there any specific characterization of kernel? Or how to recognize that a typical function is a kernel?
So if I rephrase a little bit, are you asking in general, if I give you a statistical problem,
Yeah.
is there a way to know whether or not it's a kernel?
Yeah.
That's your question. Okay. So actually, it's a very good question. When you do kernel theory, so you learn the whole theory, and then you're in front of a new problem, and you ask yourself, is it a kernel or is it not? So what I would say is that there is simple ways to see when a problem is not a kernel, okay? Because here, you see that for it to be a kernel, it has to have this form. So minimize a data loss plus a loss that's going to be a L2 norm in some kind of abstract space that you don't know of, basically. But there are very simple ways to see whether or not a norm is given by a scalar product using what's called the polarization equations. So you know that when you have a norm, if it's given by some kind of scalar product, then you can reconstruct the scalar product using this norm, using the polarization equation. Okay, it's just saying that the L2 norm of x plus y, it's the L2 norm of x plus the L2 norm of y plus twice the scalar product. Okay, and so when you have all the other norms, you deduce the scalar product. And so if this norm does not satisfy this polarization equations, then you are sure that it's not given by any scalar products in any space possible. And so it cannot be a kernel problem. Reversely, so you have a very generic way to see whether or not a problem is a kernel. But then if it satisfies the polar identity, then what's difficult is to check whether or not you can construct a map or find an appropriate kernel, and whether or not the map that you're trying to reconstruct is interesting in the sense that it's not trivial. I mean, that was the idea of the whole RKHS space, saying like, for example, if your norm is 0, then 0 is given by a scalar product. I mean, it's always 0. The scalar product of x and y is 0. Okay, great. But then the space of functions that are represented by this scalar product is always 0. And so it's not very interesting as a space of study. Okay, so that's the difficult point in kernel, is to find to characterize the RKHS and to say whether or not it's an interesting kernel that are going to give interesting functions in the end.
Okay, so I have 2 more questions. If you can,
right. Go ahead.
Yeah. So I am a self-learner. I'm trying to learn about the physics informed neural network, but I don't understand the physics you incorporate, the PD you are incorporating in the training, in the loss function. Because, for example, if you think about the heat equation, and you're trying to solve the heat, but you're trying to find the function u. For example, if you have ut plus minus c squared ux squared. So now, how do you incorporate the derivative inside the because it's the function that you are looking for?
Yes, definitely. So in your example, you want to find a function that fits your data and that satisfies the heat equation, if I understand it well. And so here the PINN framework, what it says is that, okay, so you have a domain that potentially has a complex geometry, okay? So here you see that the domain in gray over there, it's not a square or a circle, it's a domain. I mean, you want to find, you have some data points there that you can represent by the orange dots. And you want to find the function that is going to satisfy the heat equation and to take into account your data the best possible way. What the PINN does is that you sample a lot of points inside of your domain, omega, that are the yellow crosses there, here in the figure. And potentially, if you have some boundary condition, you sample the blue crosses there on the edge of your domain. That's the first step. And then what the PINN does actually is very simple, is that it wants to find a neural network that is going to satisfy the boundary condition at the given blue crosses, and so that its derivatives satisfy the heat equation at the yellow crosses. And so to do that, you find the neural network that minimizes the forwarding risk, that is the gap between its evaluation at the data points and the true measurement that you've made, plus the gap between its value on the edge and the value that you expected in your model, plus the fact that its derivatives do not satisfy the heat equation on the yellow crosses. Is it clearer now, or is it still a bit blurry?
Yeah, okay, yeah, okay, thanks. Yeah, I see. My other question is about the Sobolev minimax rate. So I can see, like, it still depends on the dimension of the input. I think the D is the dimension of the input, right?
Yes, definitely, yes.
Yeah, so it seems like it doesn't solve the curse of dimensionality. Is it the case, or it solves the curse of dimensionality?
Sorry, what's the problem with dimension? Sorry, I didn't.
The curse of dimensionality, like your input data. So the dimension of the input data is not, so the error is not depending on the input, the dimension of the input data, so that you can use more input data. It doesn't affect the complexity of the neural network.
Yes.
So
yeah,
so
there's a certain, yeah, definitely. So as I said before, the kernel methods is such that the whole complexity of generating the optimal function f hat of n is independent of the dimension of the problem. That's true, but you're going to pay it in the end because the error that you made depends in itself of the dimension of the problem here. That's true. You see that the higher the dimension, the worse the error is. And you have some kind of a curse of the dimension here, because if you want to achieve a given error, then it grows, the number of points that you need to sample grows exponentially in the dimension. That's true.
Yeah, so my problem was, so why do we need the physics-informed machine learning instead of the classical approximation?
Why do you need the physics-informed machine learning in the approximation of what? Sorry.
Like the finite element method to approximate PD, or
okay.
finite volume. So
okay. So here it's the first setting. You remember? I'm going back. So I told you that PINNs could be used for 3 use cases. So the first one is to solve PD directly. The second one is for hybrid modeling, and the third one is for inverse problem. Okay, and that's true that in the PD solver case, the PINN technique, fixed informed neural networks, is a direct competitor of other techniques such as finite element methods, Runge-Kutta, or other things that you can think of.
Yeah.
And it's a legitimate question to ask whether or not it's useful, it's best, in which cases it's more interesting, in which cases it's less interesting. So here, the talk is focused on the hybrid modeling case, okay? And as I said, it's a nilpost problem. And so all the finite element method things, all the things from the PD communities cannot be applied in this setting. And so that's why I think it's interesting in itself, because it's a new thing that tackles new problem. Whereas in the PD solver case, it's true that it's unclear when the PINNs are more interesting than traditional methods. It's true. What I can tell you is that people, practitioners, they are interested in PINNs for the following cases. Whenever you have a high-dimensional domain, it seems that physics-informed neural networks, they perform better than traditional techniques. This is not shown in my results, in my theoretical results that I presented to you. It does not appear. I didn't manage to prove it, but it seems that experimentally, in high-dimensional volumes, things like that, PINNs perform better than other techniques. It's also interesting because here I've shown that, well, you can see the PD solver case as a hybrid modeling case where there's no noise. I mean, so when you have a result on hybrid modeling, you directly have it for the PD solver case. And what's interesting is that the PINNs is always going to converge toward the solution of your partial differential equation, regardless of the way you sample the points. They just need to be all over the domain and taken randomly. Whereas for traditional techniques, there is plenty of ways to do some interesting meshes, particularly where there's some breaking points. For example, in you have plenty of nonlinear PDEs where you need to sample a lot of points in a very small region of the space, rather than some other. It's not that useful. Okay. And so when you're doing PINNs, you do not need to worry about that. You can sample your points everywhere, and it's going to converge. The setbacks, though, is that you need to suppose that you have a regularity in the solution of your PDE. You see here the result that I gave. You need to suppose that, I don't know if it appears somewhere, sorry, but that to have the convergence, you need your solution to be in the Sobolev space of some order, and so you need it to be smooth. Whereas some PDE practitioners want to study PDEs where the solution is less smooth than that. And so it's unclear whether or not actually the whole idea of penalizing the L2 norm of the derivatives is a good idea. So there's this debate. It's an interesting one, but I'm not special enough in PDE to give some interesting insights regarding this.
Okay, thank you. But you said if someone wants to reach you, your website, but I didn't see your website. So I want to discuss with you more about after and how to reach you out.
You want me to show you my website? That's the question?
Yeah,
Yeah,
just
because I want to reach you out after this.
Oh, yeah,
Discuss, yeah.
okay, so I'm going to show you.
who might ask question?
Okay, thank you. Thank you. I finished my question. Thanks.
Okay, so just I do that, and so you take Nathan Doumèche. You go there, and so you have my email over there. And if you
Okay,
want to
thanks.
have the slide of the seminar of today, you can click on so you go on research and teaching, and you can click on this link over there, and you have all the slides.
Okay, thanks. Thanks a lot.
Thank you. Yeah, you had a question, sir. Sorry.
A few comments, Nathan. Nice talk. So
Thank you.
first, you can make a very simple connection between solving and learning PDEs and kernel methods via the perspective of optimal recovery. And it gives you a very simple proof of convergence. So in optimal recovery, what you do is that you minimize the RKHS norm of your approximant subject to the PDE being satisfied at collocation points. So this tells you that the RKHS norm of the approximant is always smaller than RKHS norm of the true solution. Therefore, this gives you compactness that is uniform in the number of collocation points. Once you add that compactness to the fact that the collocation points become dense in the domain, you get convergence. So it's 3 lines of proof.
Okay.
You can also get error estimates very simply in a very similar manner. The only thing that you really need to assume is that the operator defined by your PDE is stable and its inverse is also stable. And if you combine this with this RKHS norm minimization, and you combine this with interpolation inequalities, you get error rates that exhibit a trade-off between the regularity of the solution and the strength of the norm that you are using to measure accuracy. The interesting thing in that trade-off is that if you make the problem very regular, the curse of dimensionality disappears. Now, on the comment that you mentioned that neural networks or deep learning methods seem to break it, we kind of don't agree about that, because our observation has been that in the setting where those neural network methods perform well in high dimensional settings, the methods will also perform well. And it has to do with the fact that those settings are settings where the underlying functions are nearly constant or extremely regular. The interesting thing is that if you use a kernel method, you will see it through the hyperparameter of the kernel. So you can use you can use, for instance, a Gaussian kernel, and you can tune the hyperparameter, and you will see that the width of the Gaussian kernel will go towards infinity, or will be like 200, whereas the domain is of size 1. And this will tell you that the underlying solution is nearly constant.
Okay.
We have seen this in some,
the case that you're referring to, is it the PD solving or is the hybrid modeling?
This is the PD solving. I'm specifically referring to the paper by Wine and on solving high-dimensional Hamilton-Jacobi PDs.
Oh,
I think this is in dimension 200. We tried it with Gaussian kernel, get same accuracy, but you get better convergence. And you can see in your Gaussian kernel that the solution is nearly constant. Another point is that, so this is following up on what we discussed on this convergence rates. I think you can get better convergence rates if you actually enforce the PDE exactly, which you can, because in practice you don't have noise when you solve PDEs, right? The only reason why you will hide noise is for numerical stability.
I mean, when you have true measurements, usually you have noise. I mean, in the
okay, so if you're trying to solve an inverse problem, so if you're not just trying to solve, because you can use PINNs or neural networks for either solving PDEs or solving and learning PDEs at the same time.
Definitely.
But if you do it for learning PDEs, then I agree with you. You may have noise, and then you will have a floor induced by the noise. Another comment on improving convergence rates by informing the kernel method about the physics, you will find results like that in the numerical homogenization community, where there has been made connections with kernel methods, and this has to do with the misspecification of the kernel. So in that community, you can show that if your PDE is rough, or if it has rough coefficients, Regular finite element methods can be arbitrarily slow to converge. Whereas if you use a physics-informed kernel, which is a bit like the kernel that you are showing, so the way you get those kernels is by essentially creating a white noise as a source term and getting the kernel of the GP induced on the solution to get your solution. And this kind of kernels will give you the minimax convergence rate in energy norm. So this is again connected with optimal recovery. It has to do with the
What was the name of the domain you said? Numerical
homogenization. If you Google Bayesian numerical homogenization, you will find this kind of references. Yeah, that's it.
Well, thank you.
All right, thank you. Any other questions or comments?
Yeah, I was wondering if this PINN approach is not aimed at the physics or difficult inverse problems. It's only trying to exploit known examples to guide the machine learning and to make it, say, more efficient.
So you're asking whether or not
the goal is not the physics of the inverse problems. The goal is to show that the hybrid, the combination of the two, is like exploiting the physics guidance. So the neural network or the machine learning methodologies, techniques will not go too wild or consume too much time.
yeah, definitely. Yeah, that's one of the aspects of it.
Okay, so now I have a maybe outside of your talk question. Can the neural network be modeled straight by physics? In other words, I know people who do the mathematics of machine learning, and they explore it with different ways. And yes, they are hitting inverse problems and so on. But maybe a physics approach to going layer by layer and all this, writing equations for that process can that. Do you know anybody who is doing that kind of approach?
So if I think you're asking a very, I don't want to talk for you, but yeah, it's a very interesting question because here you're right that the physics is enforced in the loss in the setting that I've presented. You want to find the function represented by a neural network
Right.
that minimizes the loss, but and this is true. You could ask to enforce the physics directly in the architecture of the neural network, for example. So
and maybe we will find new, more elegant, efficient architectures.
yes, definitely. That's a very interesting avenue of research in the physics informed machine learning community. So what people are doing is that sometimes, so there is not like another commonly used algorithm, very different from the one that I've presented to you, that uses the physics in the architecture in itself. But I've seen some people thinking about it, and so sometimes, for example, they add some Fourier decomposition inside the neural networks so that it can work directly on the Fourier space. And also, an interesting thing that I've seen recently is that sometimes your PDE is symmetric or translation invariant or things like that. And so people are trying to build some neural networks that satisfy the symmetry or the translation invariance of the PD given. So it's very interesting, and it's still a bit new and springing everywhere. But yeah, that's definitely a very interesting question. But regarding the theoretical results, I haven't seen any regarding this very question. I haven't seen some people seeing that if the PD is translation invariant, then using a translation invariant neural network will speed up the process. And to be able to quantify it somehow, I have not seen it right now, but it would be very interesting. I agree. Yeah.
Thank you very much. Wonderful talk. Thank you.
Thank you, sir.
Yeah, go ahead, Roman. Yeah.
I did a reference on that very question, but from the perspective of kernel methods. So for Navier-Stokes equations, you can create a kernel such that its RKHS space is divergence-free. It satisfies the boundary conditions, non-trivial ones, and it encodes the Kolmogorov-41 scaling laws into the kernel. And you can see by using a physics-informed kernel like this, you actually improve convergence rates.
Oh, great.
Another comment is that if you look at the very beginning of the talk where you were adding this L2 regularization on the weights and biases of the neural network,
definitely.
And if you assume that your neural network has only one layer, this is exactly an RKHS norm minimization. So you essentially recover the setting of optimal recovery. So optimal recovery is simply you minimize the RKHS norm subject to strong or lax constraints on the PDE. And if your neural network has only one layer, that L2 norm of regularization on theta is exactly doing that. It's enforcing the minimization of the RKHS norm. In fact, you can show that without this minimization, meaning if your approximant is actually not minimizing the RKHS norm, it will induce a lower bound on the error. Therefore, what these neural networks methods are doing implicitly is the RKHS norm minimization that you are making explicit via theta.
It's a very interesting comment. I have a remark is that I don't know whether or not it's structural to the neural network, but the fact that a neural network is able both to approximate a function and its derivatives, it's only be proven for neural networks with at least 2 layers. So I don't know whether or not it relates to your setting, but so here in the paper we suppose that too. But yeah, there might be some kind of approximation problem with the neural networks with only one layer. But I don't know.
With one layer, you get a feature map, right? So you essentially recover a kernel method. So the thing is that you have to put the non-linearity first and the linear part after. So you reverse. So in a neural network, you do linear, non-linearity, linear. Reverse that order. So when I say non-linearity, you put your non-linearity first and then you put the linear part. So essentially what you are using is
that's a kernel joke thing, yeah, of course. But I'm not, I'm thinking if you do that, I'm not sure whether or not it's more useful to do that just to do a linear regression in itself. I mean, because you're just deforming the coordinate with some kind of activation function, but and then you do a linear regression on the coordinate.
That's it. That's it. It's just so optimal recovery is linear regression. It's a kernel method, right? So you have this equivalence between optimal recovery, Gaussian process regression.
Then you have a bias. If you're doing just linear regression, I mean, you cannot. You have an approximation problem with the, in the sense that it cannot approximate arbitrarily well any smooth function.
Yeah, you're limited by the number of basis functions that you use.
Yes, definitely. Yeah. Definitely. Okay, so we agree.
But in the limit where you make your neural network infinitely wide, then you can approximate anything.
Okay.
But you will recover a non-degenerate kernel.
Great.
All right. Any other questions or comments? So I had maybe just a quick question about the PDE for the kernel that you had. Can you just show it?
So the PDE, the last one,
the last, but yeah, exactly.
So it's very simple. It's only d over dx. I mean, it's the simplest one that you can think of.
Yeah, but I'm talking about the general PDE that you got, the one I think before it, or is it?
Ooh, I mean in the polynomial operators, you mean?
Yeah, exactly. Yeah.
Over there, when I said that pins are consistent for all polynomial operators.
Yeah, okay, maybe I'll ask you about it later, but because I saw some PDE that you were solving for the kernel.
Oh, the PDE of the kernel. Okay.
Yeah.
Okay. It's over there. This one.
Yeah, so that one. I mean, here, do you think that it would be easier? I don't know. Like if you instead of looking for the PDE of a kernel, maybe you can look for something for the feature map. For the phi instead of the k, and then the phi may also help you to construct a good neural network, because neural networks are also approximating feature maps, right? What do you think?
So that's an interesting question. So here, the feature map is this operator over there. So we can, I mean, it's given by that. The difficulty is to compute it. We can give a name to something. It's not easy to see. Okay, so the thing is that computing this kernel, or reversely computing the map, in general, it's more difficult than solving the PDE that you've enforced. So I don't know whether or not you're familiar with weak PDEs, but it's very simple. The idea is just that if you say that something satisfies a PDE, then you integrate it over a test function, and you can write the PDE differently. Okay, and so here you see that the kernel K, so it satisfies the PDE due to the Sobolev norm. So okay, whatever, but it also depends on the operator D over there. And so typically you would have that the PDE given here is that the adjoint of D applied to D of K is equal to 0. Okay, and so for example, if D was a gradient, you would end up with a Laplacian in the end. So you double the order. If you see gradient is of order 1, Laplacian is of order 2. If you had a Laplacian, you would have Laplacian square in the end. And you would know that Laplacian square of D would equal to 0, more or less the Sobolev thing. Okay. And so solving this PDE for the kernel is hard, and it's harder than your initial problem, actually. And so this is why we've done it for d over dx, because you got d squared over the x squared, so that I can manage. But if you enter high dimensional operators, it's going to get more tricky. And I mean the map. You know that the maps in the RKHS, it's always the k of x dot. See, it's written like over there.
But this is only like one map. Is Aaron-Jones canonical feature map, but you may have other maps that you get through Mercer theorem, and so you see what I mean. That if because here you see, so this is like only one particular map, feature map, which is like Aaron-Jones canonical feature map. But assume that you go through Mercer theorem, and so you get the phis that are obtained as the eigenfunctions of the integral operator.
Yes.
Yeah. So I was wondering. So I'm just wondering if like a different reformulation of the PDE using feature maps wouldn't be better, just because it will allow you also to construct a neural network, right? Because neural networks in a way are just like feature map approximators.
Yeah, of course you can try to, but the difficulty is that some PDEs they don't have explicit solution. I mean, solution that you can write as usual function, like a cosine, exponential, something like that. I mean, if you think, for example, of the Laplacian over some domain that's not a square of a ball, then you can show that the solution is not, the green function is not expressive. It cannot be written simply. And so, yeah, this would be a very interesting idea to take the eigenfunction of the kernel, use them as a feature representation instead of the neural networks, and fit basically the what would be the eigenvalues, but in this case the parameters of your regression. But to do that, you need to be able to compute quickly this eigenfunction. And so in dimension 1, it's not a problem because it's so, I mean, you could, for linear PDEs, for example, with constant confusion, it's always exponential. But in dimension 2, even with constant coefficient like the Laplacian, if you are studying a complex geometry, it will get more difficult, I think, too. But perhaps you can approximate them with some series with a quick decay rate, but that would be sophisticated method that I'm not aware of. But I mean, it would be great.
Yeah, but maybe we should continue discussion offline with Uma. Yeah. Yeah. Thank you very much. It's a very nice talk. Any last questions? I think we kept you for 2 hours. I think that's a good enough. Yeah. Anyway, thanks a lot. Thank you very much for the very nice talk. Yeah, thank you.
Thank you. I was very happy to present it.
Yeah, thanks. Bye, everyone. Thank you.
Goodbye.